Right, hello guys, welcome. Please let me know if you are here. If you cannot access the chat while we are live for any reason, please send me a message and show my homework, and then I can see that you have turned up for the live chat, for the live stream. So if you are joining me not live, then obviously you are not able to see the chat straight away. If you wait a couple of hours, it should appear so you can still see what's going on after the live stream is actually finished. But please let me know you're here so I can give you that point on show my homework. Okay, so we're continuing today with algorithms. Okay, we're continuing with this idea of algorithms. Last lesson, we talked a bit about having different algorithms. How do we represent algorithms with so let me get this up for you so that you can see it. Where did it go? Change that. Okay, so let me get that up. Yeah, sorry, I hadn't got it up there. Last lesson we we understood the idea of what an algorithm was. We looked at the different algorithms in terms of their inputs, processing, and outputs. And we were looking at the differences between pseudocode, flowcharts, and code, as in Python code. All right. So this lesson, we're going to continue with our algorithms idea. But first, before we're going to start, I'd like to ask you this question. So in the chat, that's my little icon for please post in the chat. Think of some different ways you could travel to get to London. Obviously right now it's not possible to do this, but imagine this was a few months ago where we were allowed to travel to London. What different ways are there that you could travel to get to London? And thinking about that, what would be the most efficient way of traveling to London? And then what do you mean by the word efficient? So in the chat, please, we've already got one answer of flight. So that's one way of getting there. But what other ways could there be? And what could be the most efficient way? What do you think the most efficient way is? Okay, so I'll give you a few moments. In fact, we'll put on a quick little song. Very quick one. Don't forget to answer what you mean by the word efficient as well. Right, so there are a few different answers we've gotten here, which is fantastic because that's exactly what I expected. So the word efficient, when we're talking about efficiency, we could talk about the different types of efficiency here, because some people have mentioned getting there fastest, so the time that it takes to travel, that could be the most efficient. We could be talking about efficiency in terms of time. We could be talking about efficiency in terms of cost, how cheap it is. So in that case, the train would be the most efficient, probably, because it's pretty fast, it's relatively cheap. In terms of time, flight would be the fastest because you can get there really quickly on a plane. Whereas you could also talk about how inconvenient it is to you, how efficient it is to get there. It might be easier for you as a family to just jump in your car and travel down to London. It might be a lot easier to travel and therefore more convenient, more efficient to travel by car. So the word efficient can mean different things depending on how much, depending on what you personally mean it for it to be. So if we're talking scientifically, yes, it's a ratio between energy out and energy put in, or the energy that could be replaced, yes. But in terms of efficiency of, there's lots of different types of efficiency is the point I'm trying to make here. So today we're going to talk about, surprise, surprise, efficiency of algorithms. And we need to, today hopefully we're going to understand that more than one algorithm can be used to solve the same problem. Okay. Now, this word efficient means to perform or function in the best possible manner with the least waste of time or effort efficiently. Okay, so that's what it mentions here on the dictionary.com. You need to be paying attention if you're going to get your mark and join in. Space efficiency. So hang on, let me go back to this. So this idea of efficiency. We've got, as I've already mentioned, there are lots of different types of efficiency. So when we're talking about algorithms, there are a couple of different types we can talk about here. So space efficiency is the first one I want to talk about. If an algorithm takes up fewer lines of code, it's said to be space efficient. So that's where if you've got a program that is on 20 lines of code, then that's not as space efficient as an algorithm that is on, say, 5 lines of code. Obviously, that is much more efficient, something with 5 lines of code. So, with that in mind, how could you create an algorithm to add all the numbers from 1 to 10? Well, you could do something as simple as this, where you add up all of your numbers from 0 to 10. You've got number equals 0, number is number plus 1, number is number plus 2, number is number plus 3, etc., etc. This is our sequence, line after line. Okay. Now, you can see straight away that this is not a very efficient way of doing it, because there's a lot of lines here. Each line you're kind of repeating yourself an awful lot. So what other ways could we do this? Okay, if you think about how would we then do this for adding all the numbers up from 0 to 100? That could get very repetitive. It would take a very long time just to even write all that in. Okay, so can you think of a better way of performing this kind of algorithm? What could we use instead? I'm asking you in the chat here, if that wasn't clear. Make sure it's clear who you are if your username is not the same as your actual name, because otherwise I don't know who you are. So what ways could we perform this algorithm? Come on, I know you know. Yeah, a for loop would be one, or even a while loop, some form of loop. Okay, so here is a while loop, okay, where we're adding up all of our numbers from 1 to 10. We've got our count is 0, our number is 0. While the count is less than or equal to 10, our number becomes number plus count, which is effectively what we were doing on the last slide. But instead of having to write in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can write in count. Okay, and yes, we could do this in a for loop or a while loop. Yeah, and if we made it a for loop, it would be slightly more space efficient, which is something I haven't actually added into this. But the count wouldn't need to be there because it would be involved in the for part of the loop. And so, could you then change this algorithm so that you're adding all the numbers from 0 to 1000? Yes, it would be very easy to do that. All you'd have to do is change this number here to 1000. You'd only have to change one thing to be able to change that algorithm. Whereas this previous one, can you imagine trying to count to 1000 using that that algorithm? Is far too complicated. Now, is there an even better way of performing this kind of algorithm? You're thinking adding up numbers. Is there an easier way of doing it rather than going 1 plus 2 is 3 and then 3 plus 3 is 6 and then 6 plus etc etc? How is there an easier way of doing it? Again, asking the chat. If you're not sure, tell me. If you are sure, yeah, so we could use our for loop instead, but so I've already mentioned that could be an option, but even easier than that, even better, even more space efficient than a for loop. Just give you a couple of seconds before I just give you the answer, because I want you to use those brains. I know you're at home, but I want you to be able to think about some different ways of doing this, because this is the kind of thing which is very useful when it comes to programming, being able to think of different ways of performing algorithms. How would you use an if statement? Or are you just guessing? So if you think mathematically on this one, if you think about how mathematically you might add up all numbers from 1 to 10 or 1 to a given number. Mathematically. I'm expecting Fraser to jump in here with his maths brain. So this is that's still using a while loop. And that would actually create an infinite loop, assuming, well, it would only run once even. It wouldn't, because your number. Okay, I'll give it to you then. If you even Fraser can't work it out, I'll show you all. Okay, so here is an equation you could use. Okay, now this is just 3 lines of code, but it does exactly the same thing. So I'm going to talk you through it. Your number is 10. I mean, you could just write in 10 on all of these, but to make it a little bit easier, we can use this as our constant rather than just any old variable. This number doesn't ever change in the running of the program, does it? So it's our constant. Our result becomes our number times our number divided by 2 plus our number divided by 2. Okay, so let's try it out. So if we were to go 10 times 10, so 10 times 10 is 100, divided by 2, and then add number divided by 2. So is 5. So our answer there is, oh, I've just forgotten what this was, 55. Okay, so the number would be 55. Okay. So you can use a for loop, but an easier way, a much more space efficient way, is to use an equation. Okay. Now, obviously, before we used a for loop, a while loop even, but we can use a for loop, which is slightly more space efficient, but it's not quite as space efficient as this here. Okay. Now, you can calculate this yourself. So if I was to go into a new tab and do 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 gives us 55, which is the same as, let's put this in brackets, 10 times 10 divided by 2 plus 10 divided by 2. I think, is that all of the brackets there? I think so. Is 55. So it gives us the same answer, as you can see there. Yeah. So this is very, very clearly more space efficient because there is fewer lines of code there. Yeah. Okay. So could you change this algorithm so you're adding all the numbers from 0 to 1 million? Yes, very easily. All you'd have to do is change the value of this constant. Yeah. So much, much easier to deal with than if you had just left it with, if you can imagine back to this algorithm here, if you tried to do that to 1 million, you would be there for a very long time. And yes, it would be fairly easy to, sorry, yes, it'd be fairly easy to change this to 1 million, but it might take a bit longer than if you were to do it for this equation. Now, talking, hang on, so you can see that the program becomes more space efficient as it uses fewer lines of code. So talking of how long it takes, there's also the other type of efficiency. So earlier we were talking about different kinds of efficiency. So for example, the difference between taking a plane, a train, or a car to London, they're all different forms of efficiency. So we've talked about space efficiency already, but there's also the idea of time efficiency. Now, if an algorithm executes in a shorter space of time, it is said to be more time efficient. Now, generally, when we're working at our kind of level, at GCSE level, we don't tend to have very many issues with how quickly our code takes to run, because we're generally running very, very quick bits of code. But if you can imagine when we're running code that is for a bank, for example, if you can imagine how many people, how many customers use a big bank, and how many different things they're going to have to use if they're looking through all of their transactions, for example. Okay, so this is really important for big businesses where they have lots of data they have to sift through. Okay, so we've got these same addition algorithms that we just talked about, and I want you to think about which of these two algorithms do you think runs the fastest and why? I'm going to give you a couple of minutes. Again, I'll play another quick song just to get you to think about and give me an answer. Which of the two algorithms do you think run the fastest and why? I was expecting to hear answers of Y or see answers of Y rather than just say, yeah, this is the one I think runs the fastest. Why do you think it runs the fastest? We've got two different kinds of algorithms. Yes, the loop has a lot more space taken up. But okay, Thomas has given an answer. The loop, as it has to check, add, whereas the equation has to times, divide, add, divide. So Tom thinks that the loop is quicker because it's got to do addition, whereas the equation has to times and divide, which is a bit more complicated than adding. Okay. Fraser thinks that using an equation uses less lines of code. That shouldn't make a difference to how quickly it runs. And the while loop would have to run 1,000,000 times, whereas the equation only has to run once. Good. Okay, so that is where our time efficiency comes in. So I'm going to show you this running. So I've got here the same code. It's a bit more complicated because I've added in a little bit too, but you can see here that this is pretty much the exact same. I've just added in a timer to calculate how long it takes, and I've added in some formatting there so that it's a bit prettier to look at than if it wasn't before. So I'm going to run this, show you what it looks like. So using a loop, it shows us that the total is that many. Obviously this is calculating for 1,000,000, isn't it? So it's calculating up to 1,000,000. It took 1.903 blah 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 seconds. Okay, whereas using an equation, same total as the loop, but it took far less time than it did to use a loop. Now you can see here that these that I'm going to a lot of decimal places just to be able to show you just how little time it takes. Now I went to this last decimal place. I went to, I think it's 10 decimal places here, because if you were to put a 1 in just that column there with nothing else, 0.0000, and then a 1 at the very end here, that would be the same as 1 tick on the clock. So before we've talked about the CPU and the clock speed. 1 tick on the clock would take that many seconds, at least for my computer, because that's, if I look at how many gigahertz my computer has, I would get that up, but I've forgotten where to put it. In fact, no, I will get it up. Properties. Yeah, so you can see here, just about, if your screens are big enough, that my clock speed is 3.5 gigahertz. You wouldn't be able to see this on the computers at school, but the one at home I can see it on. 3.5 gigahertz, that is my computer, the clock speed of my computer. And if I was to leave put a 1 just there, that would be about how many seconds it would take to complete 1 tick on the clock, as in on the clock of my computer running at 3.5 gigahertz. That's 3.5 billion, processes per second. Okay, so now I think that was correct. That's what we worked out. But so that showed us that was much quicker than it would have been if it had just been our loop. So as Fraser had mentioned, the while loop has to run 1,000,000 times. Like this part of the code still has to run 1,000,000 times, and actually there are 2 lines of code here that are both being run because it's in a loop. So actually, we're having to do 2 million different things, 2 million different calculations there. Whereas in the equation, we only have to do one calculation, even if there's quite a few extra bits to it. Okay, so hopefully that allowed you to kind of see the differences between using a loop and using an equation and how much faster that is. Now, if you look at the differences between these, this 1 point whatever seconds, it may not seem like a lot, 1.9 seconds, if you're running a million things. But if you think about processes, programs where they have to go through billions of things and go through billions of things however many times in a day, that will add up, and it gets there it makes a huge difference having an equation or an algorithm, that is more time efficient. Okay, so this is an earlier running of the program. As you can see, it's not quite the same each time. So this time it took 2.15 seconds and 2100 seconds instead of 2000 seconds. Yeah. The amount of seconds will change depending on what different just different things that are happening with the computer at the same time. So obviously my computer wasn't running as many things at once this time round as it was last time round, perhaps. Maybe that's why it was slightly faster. Okay. Why is one algorithm quicker than the other? Well, we've established already that this algorithm here, the loop has to calculate different things, has to go through each of these lines of code, and it has to still run this line of code a million times, whereas this line of code only has to be run once. Yeah. So in the chat, I would like you to give me 5 trues or falses based on these different things. So if an algorithm executes in a shorter space of time, it is said to be more space efficient. Can you make sure it's clear which ones you are answering? So maybe put 1, true or false, 2, true or false, etc. 3, 4, 5, 6, 7. Sorry, 5, up to 5, not 6 and 7. But answering those questions using the numbers as well, rather than just putting true and false, because otherwise there's too much that could be different there. Okay, too much that could be confusing. Apologies. So I'll give you a couple more minutes to look at that and type that into the chat. Right, so few answers here, which is good. So we've got, if an algorithm executes in a shorter space of time, it is said to be more space efficient. That is false. Space efficiency is not about how long it takes, but in the idea of how many lines of code it takes up. So your shorter space of time, that was a bit of a red herring there, okay? So if an algorithm executes and takes more time, it is said to be time efficient. That is also true. Another little red herring. If it takes more time, it's not very efficient, is it? It's going to take longer, which isn't very good. Okay. Number 3, a loop is a good way of making a program more space and time efficient. It is true. It is a good way of making a program more space and time efficient than, say, the first way we've got it. It's a way of making a program more space and time efficient. It's not the only way to make a program more space and time efficient. It is not the way to make it the most efficient always. Sometimes it is a way of making it more space and time efficient. And most of the time, it's much better than if you were to just leave it with simple, just having a line-by-line sequence. Number 4, a program that executes in 5 seconds compared to a program that executes in 3 seconds is said to be less time efficient. That is true because it is taking longer. Number 5, sometimes a simple equation can be used to arrive at a result, making the program more efficient. Again, true. That won't always be the case. But if you're doing a loop that just does a simple addition, for example, or if you're doing some sort of calculation, mathematical calculation, then often an equation is the best bet. But that won't always be the case. It won't always be possible for you to use an equation to make your program more efficient. Okay? So, we have looked at the efficiency of algorithms, and we have understood that more than one algorithm can be used to solve the same problem. Now we've still got a good 25 minutes before the end of this live stream, so I am gonna just quickly go on to the next thing I wanted to talk about, which is the idea of linear and binary search algorithms. We have already talked about this before. We have done a lesson on this before, but I just wanted to recap really quickly. So I haven't edited this lesson to make sure it works for live stream, so apologies if there are a couple of bits where it's asking you to do something you'd be doing in class. So you've got your linear search. A reminder that the algorithm you're using for a linear search, you're looking through a list of data, one item at a time. If we think back to what we've just been talking about, you can see straight away that this is not a very efficient way of doing it. Trying to search for something going through one item at a time, not very efficient. So because our algorithm's very simple, it's not very efficient. If you think about when you first started learning to program, an algorithm like that first addition one would have been the kind of thing that you would have written probably. Whereas now you've learnt about loops and you've learnt a little bit about other ways of making things more efficient. So we're talking about typical situations where you might want to use computers to automate a search through a large amount of data. So school, for example, looking for an individual student's name in a set of student records, or in banking, you're looking for a customer's account number using a bank database. Now, in a school, you could have thousands of possible records if you've got a large secondary school or college. And in a bank, you could have hundreds of thousands or even millions of records if you're in a well-known national UK bank, or even not nationwide, international bank. Okay. So our linear search algorithm, this is our pseudocode for linear search. We've got our search term becoming user input. So in Python, we would just say equals, search term equals user input. Our match is false. This is what we call a flag. It's basically saying, is it or isn't it? It's a Boolean value. At the beginning, we set that to false because we're basically saying, at the beginning, we haven't found a match yet. So we're calling this variable here match so that we can say, yes, we have found it when we found it, or no, we haven't found it if we haven't found it. And our record number is 1 because we're looking at the first record. And then we're going to do. So do until is another form of loop that you could use in other programming languages. In Python, we don't have a do until loop. Do until makes sure that the first one the code runs at least once. Whereas in Python, it's not possible to make sure that your code will always run at least once, which is why sometimes we have things like having to write the same code more than once to do something like validation. Okay, so compare the current record with the search term. You can see here this pseudocode is basically English. Okay, you're not saying that you're not having to write in Python, but you can write in English to see. Look at the difference between current record and the search term. If the current record matches the search term, then our match is true. If the current record is equal to the search term, then the match is true. And then our record number becomes record number plus 1. And this is the case, and we're going to do that until the end of record set is reached or the match is true. So it's going to keep going until it finds the correct item, or until it's gone through the entire list and gone, oh no, I've not found it. So and then after that loop has finished, it's going to say if the match is true, then it will print out record found. Otherwise, it will say record not found. Okay. Now you can imagine, I remember when I last spoke to you about this, I was talking about picking up a book and trying to go through page by page and being able to go, well, is it this one? No. Is it this one? No. Is it this one? No. Is it this one? And this takes a long time. Now, best case scenario on a linear search algorithm, it is the first item you look at. Worst case scenario, it is either the last item you look at or it's not there at all. Okay, so if we look at this list sheep, going cat, dog, sheep, we're looking for the item sheep, cat, dog, sheep, giraffe, mouse, elephant, zebra, cow, position of item in the list, value of item. So is number 1 sheep? So it looks there. Is number 1 sheep? No. Is number 2 sheep? No. Is number 3 sheep? Yes. So its match is equal to true. So now it's going into match is equal to true, and the record has been found. So if we were to go through this second one, the match is equal to false. Our search term is Fred, and the record number is 1. So if we start, whoops, because this one was one that I wanted you to do in class, but obviously we're not in class, so that's a bit harder for us to do. But hopefully you can kind of see straight away that we look here first. Is James equal to Fred? No. Okay, move along. Is Alan equal to Fred? No. Is Maisie equal to Fred? No. Is Fred equal to Fred? Yes. So match is true, and then the record is found. Okay. How many times did we have to run the loop? Well, minimum amount of times is 1. Maximum amount of times is the length of the list. So if we were looking for June here, then we would be going through every item in the list until we got to the final item in the list. Now, if you can imagine this was a list of 1,000 items and none of them were June apart from the last item, then you'd be going through this 1,000 times, and that's not very efficient. So next, we're going to look at the binary search algorithm. That's way more efficient than our linear search algorithm. Okay. So binary search, a reminder of what this is a method for searching data that splits your data into 2 components over and over again until you find the search term you are looking for. So a data set is a collection of data. So for example, a table in a database, or a list, for example. And why do we use the word binary? Well, binary means 2, or 2 states, and it is talking about splitting our data set into 2. Now, a binary search can only work with an ordered list. In an exam, often they will ask you about why, what is special about a binary search? What do you have to make sure is the case before you start a binary search? This is the important bit to remember. You need to have an ordered list or it won't work. So you need to make sure your fields are sorted in a specific order. So either numerically or alphabetically. So in order, in some sort of order. So you also need to know the size of the list so that you can work out what the middle of the list is. Okay. So here's our algorithm. You're looking for a certain search term. This is what the user's typing in. We're starting at value number 1. Our end value is whatever the length of the list is, or the size of the data set. We're going to do, we're finding the middle value by finding the average. So start plus end divided by 2 and then round that down. Okay, because we need to round in some way, because otherwise we're not going to have that value. So if the record that is in the middle of the list, so this is our list here. You can see that it's a list because of the square brackets. If that is less than the search term that we have looked at, so less, if we're talking about a numeric value, then that's fairly obvious. If, for example, 5 is less than 20, that would work. But if we were talking about an alphanumeric or even an alphabetic search term, and for a data set that contains words instead of numbers, then it would still work, because is the word red less than the word yellow? Yes, it is, because red comes before, or R comes before Y in the alphabet. So that's how that would work. Our start value then becomes our middle value plus 1, because the middle value, the middle value is less than the search term. So we're going to be looking at the side of the middle that is bigger than the middle. Okay, so we're going to be looking at the right-hand side rather than the left-hand side. And then if the record is more than, then we're going to say it's the end is the middle value -1. And this will happen, we'll do this over and over again until that record is equal to the search term, or the start value is equal to the end value. That means that we've got to the end of the list. So our linear search has an algorithm that is easier to understand. So it's very easy to go, check that item, does that work? No. Check that item, does that work? No. Check that item, does that work? No, etc., etc. That's easier to understand. But the binary search algorithm is more complex, but it will be much quicker because you're not having to search through every item in the list. You are halving the amount of items you are looking at any given point. Okay, so we're looking at this ordered list, goes from 0 to 99, the values that we've got, and obviously there are 21 items in our list. Okay, so we've got our positions and we've got the values of our items. Okay, so number 5 is the value of item 4. So our search algorithm, if we're using our search algorithm, our search term becomes user input, and we're going to start at 1, etc., etc. So our search term is going to be 43. We're looking for the number 43. Now, we as humans can look at that and go, it's there. That's where it is. And that's really easy for us to find because we just go, okay, we kind of do a little binary search much quicker than a computer, well, maybe not even quicker than a computer can, but we kind of look through and we go, okay, well, it can't be down there because those are small numbers, and it can't be up there because that's quite a big number. So, I can kind of see these are teen numbers, so it's got to be up around here somewhere. We kind of do the same thing in our heads when we're looking at an ordered list. So our start value is 1. Our end value is 21. So we're looking at this entire list at the moment. And our mid value is cell 11, which is 18. Okay. So is 18 equal to 43? No. So we're changing the start value. We go, okay, 18 is less than 43. So it can't be any of these items here. Okay. Bear in mind that a computer can only really look at one item at a time. It can't really look at all of these items at once. Okay. So our start value is now 12. Our start index is now 12, and our end value stays the same, 21. And now you can see it's only looking at this section of the list now. It's kind of going, this is a new list. So our start value is now 12. Our end value is 21. Our mid value, if you calculate 21 minus 12, gives you 16, which gives our not 21 minus 12, sorry, 21 plus 12 divided by 2 gives you 16, rounded down, and that's our 45 there. So is 45 equal to 43? No. So condition has not met requirements. So the end changes this time because 45 is more than 43. Okay, so instead of looking at this side of the list, because this is definitely not going to be on that side because 45 is more than 43, we know that it's going to be on this side of the list somewhere. So the end is now, so we're only looking at this part of the list now. Search time of 43, our start value is 12, our end value is 15. If you add 12 and 15 together, divided by 2, you get 13.5, round that down to make 13, and the value there is 26. Okay. Is 26 equal to 43? No, it is not equal to 43. So we are now looking at a new start value. 26 is less than 43, so we're going to go above to look at this section here. So our start value is now 14. our end value, 14 plus 15 divided by 2 is 14.5. We have to round down, so we're going into 14. And then, so is 29 equal to 43? No, it is not. So we're going to change the start value. Start value is 15. We're going to look at it. Start is 15, end is 15. Is the cell of 15 43 equal to 43? Yes, it is. If this value was not 43, if say it was 42 instead, the program still would have exited because the start is equal to the end now. Now that was the worst case scenario, but you could see that that only took us 5 steps. Okay, that only took us five runs through. So exiting that program, that was much quicker than if we had to go do a linear search, even on an ordered list, and get to value number 15. Okay, and that would have taken us 15 runs through our program instead of 5. Okay, now you might have to look back to last year's practical information. This is it says year 9 here, so you might have to go into your year 10 and back into last year's data and see if you can find your binary search information and trace table information. I again haven't optimized this for use on a live stream. I wasn't expecting the first part of the lesson to go quite so quickly, so I just wanted to make sure we had something for the next part of the lesson. I remember from last year that we didn't manage to do this, so if you can get that done and then send it to me via Show My Homework, that would be appreciated. And try and complete that trace table, try and work out how that works, go through item by item, and remember how we did trace tables. I was going to do a lesson on trace tables, but that was even less organized than this part of the lesson. So see if you can remember how to do trace tables. Next lesson, I should be going through trace tables with you, or next week anyway, not next lesson. But I'm going to leave it there so you've got enough time to go through that binary search and submit it onto this lesson on Show My Homework. So I've given you 5 minutes. You can take as long as you need, obviously, but I will see you on Wednesday. Have a lovely weekend.